Hi everyone, this is coupling A-15. So in this activity, we're going to get to learn how to read an engineering drawing that has various cylindrical features. So if you recall from our class, the two important aspects of cylindrical features are number one, the size, and number two, location. So size, I'll write that down here, and location. So how do we indicate size for cylindrical features on an engineering drawing? Well, we use a leader, which is an arrow, and if it is a cylindrical feature that in 2D looks like a complete circle, we have to use the diameter symbol. If something is a partial arc, so if I had some kind of a component like this that had a radius or a fillet, a partial arc is specified with the prefix R to indicate radius and then the size. So this could be a radius of 0.25, and this diameter symbol could be pointing to a diameter that is, say, 2.00 inches. So in this activity, we've got this object. It's called a coupling, and it's, as the name implies, it's coupling something together. It could be a pipe system, or it could be a coupling in a mechanical transmission or power train system. So this coupling has a few features that you're going to learn about. The one type of feature I want to point out to you is a feature that's called, and I'll clear my screen here, it's called a flange. So flange is a term for a feature that allows one cylindrical object to bolt to another cylindrical object. So this main body here of this coupling has a flange, a top flange here, and this flange has holes that are drilled into it, and this allows it to be bolted to an adjacent pipe or component. Likewise, on the bottom side, there is a bottom flange, which is larger in diameter, and it has, again, some holes that are drilled into it, and it can bolt to another mating component. So flanges essentially are diametral features that are increased in size from the main body, so we can allow for bolts or fasteners to pass through. Let me show you this shape in Inventor. So I've drawn this up for you in Inventor so that you can get a feel for what it looks like in 3D. So here it is. So here is the, I'll just draw to this, the top flange. This is the top flange, and this is the bottom flange. And you can see here that we can pass fasteners such as nuts and bolts through these holes. That's what their main purpose is. Okay, and then there's another feature here, this raised feature, and we would call something like this, typically, you might hear someone call this it could be either called a pad or typically a boss. Okay, so it's a raised feature that provides, so this component can be cast, and then this flat area could be machined nice and flat, and it may provide a means to mount something, like maybe there's a additional, if this isn't a piping system and we're connecting two sizes of pipes, coupling two sizes of pipes together, maybe there is a gauge or something that's going to mount to this boss. So this is what the part looks like. I'll orbit it around for you so you can see it. But eventually, when you look at these two-dimensional drawings like this, I want you to be able to get enough skills or gain enough skills to look at this 2D and picture the 3D object as you see here. So the top flange has a bit of a beveled surface here leading into the main bore of this coupling. So sometimes this is called a chamfer. And depending on the context of what we're doing, one might also argue and say this is a countersunk hole. On the other side, we have a larger bore, um, sometimes referred to as a counter bore, but we'll chat about that in a future lesson. But for now, I want you just to get some experience in interpreting the engineering drawing for this component. So back to the drawing. What we're asked to find initially in the questions, and I'll go through some of these with you now, are firstly, what are the diameters of circles A through H? So let's look at the drawing and determine what the diameters of those circles are. They're cylindrical features in real life or in 3D. They're depicted, those 3D shapes are depicted as circles on the two-dimensional drawing. So let's go through this. Let's find A and start from there. So here the leader line is pointing to circle A. Circle A happens to be a center line that is actually drawn in a circular shape. Okay, so center lines can be drawn in circular shapes to indicate a bolt hole circle in this case. So this center line is not representing, it's not a visible line, it's not representing a physical feature. It's representing a reference feature. Okay, it's reference geometry. This is something that you, as say a machinist or a fabricator, is going to use this information so that you can lay out where these holes are going to be so they're in the right location. So circle A is the bolt hole circle that's locating these holes on the top flange. Okay, this is the top flange here, if you recall, right there. So let's have a look. Let's do some investigation. So we look at the holes that are located on A, on circle A, and we see here that we have X holes. Okay, so the X is beside this hole, and we have some Y holes. Okay, so the X holes, and as indicated by this note, there are 4 of them. So there's 1, 2, 3, and 4, and they're equally spaced. EQL stands for equally spaced on a diameter 2.62. Okay, likewise, these Y holes here, there's 4 of them, they're on the same bolt hole circle, we could say. That's how we would speak in the shop. They're on the same bolt hole circle, and these are equally spaced on, of course, a 2.62 diameter. So the answer to question 1A is the diameter is 2.62. Okay, that's the question to A. Now another thing to note here, it's kind of important that the designer has used the term or the abbreviation for equally spaced. That tells us now that we don't have to look for an angular dimension. So again, the machinist is going to look at this and say, oh, there's 1, 2, 3, 4, 5, 6, 7, 8 holes on a 360 degree circle. So if I take 360 degrees and divide that by 8, what do I get? I get 45 degrees of separation between each hole. So these are 45 degrees apart. So we don't have to place an angular dimension because the holes are equally spaced, and we're just dividing a 360 degree circle by how many holes there are on that circle. So let's look for circle B. So I find circle B right here. It's again, the visible circle. It's drawn. It's representing the diameter, the OD, of the large bottom flange. And again, use your ruler. There's no, there's mostly circular features, but we still need to use a ruler to use the multi-views to help us find the information. And what we find is that we track this down to the bottom view. The size of diameter B is 4.76. So this is diameter B right here, 4.76 inches. So moving along, let's look at C. Well, C is easy. We've just done one like this before. C is another center line, which happens to be drawn as a circle. It's a bolt hole circle. And I then look at holes that are on that bolt hole circle, and there's the answer right here. There's 6 holes that are a diameter of 0.368, equally spaced on a diameter of 3.86. Now there's no mistake that the larger circle here is 3.86 and that the hole is 0.368, because it wouldn't make sense if the hole was 3.86, because the overall size of the flange is 4.76. It would be way too huge. So you read this in order. There's 6 times 6 holes that are all 0.368 inches in diameter, and they're equally spaced on a diameter 3.86 inch bolt hole circle. So the answer to C is 3.86. That's what it is. So moving along, question D, or circle D, it's the diameter of the top flange. If you use your ruler to project the lines to the bottom view, you can see right here, there's your answer. It's right there. How sweet is that? 3.5 inches in diameter. So D is equal to 3.5. So for circle E, if you use your ruler against your textbook page, you will track this feature all the way down to the 1.364 bore that's on the bottom flange. So the answer to E is 1.364. So F, circle F, is a visible line, and it's going to represent the outer diameter of this chamfer on the hole. So that is F, and that happens to be right here 1.20 inches. So F is 1.20. And I'll show you on the inventor drawing. So F is actually locating, is this diameter here. That's what F is. There it is. So the last diameter is diameter G, and it's basically the 1-inch bore that passes through the part. So here's diameter G right here on your drawing. The arrow is pointing to this visible line, and it's lining up right to that hole, and that hole is 1.00 inches. So that's G. So there we go. Those are all the circles that they asked you to identify by size. So let's look at the next question. The next question is asking how many holes are in the bottom surface. So the bottom surface, again, this is top, and therefore this surface along here is the bottom. How many holes are in that surface? So if we look, we can count, and we can say there are, well, here, let's look at the 3D part. So we look at the 3D part, I switch to the bottom. So we have 1, 2, 3, 4, 5, 6, and technically we have 7 because there's a hole through the surface here. So there's 7 holes. Now if the question said how many bolt holes are there on the flange, the answer would be 6. Okay. So that there are 7 holes that pass through that bottom surface. Let's look at the next question. How many holes are in the top surface? Okay, well that's pretty easy now. And what we're going to do is we're just going to look at the top surface and we're going to count the number of holes. We have 1, 2, 3, 4, 5, 6, 7, 8, and then the hole through the center is 9. So there's 9 holes there. It's like playing a 9-hole golf course. There's 9 holes there. Okay, so let's keep going on here. How deep is the 1-inch hole from the top of the coupling? How deep is the 1-inch hole from the top of the coupling? So if we were drilling a hole into this part, here's the 1-inch hole specified right here. This surface is the top right here. So the 1-inch hole starts, even though it has a chamfered edge, the hole starts on this visible line at the top, and the hole ends right here. That's where it ends. So we have to look a little bit deeply, we have to look deeper, pun intended, at the drawing. If you look at this bottom hole here, that it's 1.364 in diameter, there's a little telltale here whereby they tell you that it's by 0.60, and DP stands for deep. So this is 0.6 deep. So that means that this dimension here is 0.6, 0.6. So that means that the depth of the hole, we're going to take this 2.5 dimension overall, and we're just going to subtract 0.6 from that. So the answer is going to be 1.9. From here, it's getting a little messy here, to here, and that's a 9. 1.9. 1.90 to be exact. Okay, the next question. What is angle J? Let's find angle J on the drawing. And here it is. Here's angle J right there. So we have a hole. Okay, so this is the hole in the bottom flange. There are 6 holes. So we take 360 and we divide by 6. That means that the distance, the angular distance between holes is 60 degrees. This is 60. I know it's a little messy the way I've drawn it with my mouse. That's 60. If that's 60, then half of 60, because this line bisects the angle, this is 30. So the answer is 30 degrees. Angle J is J equals 30 degrees. There it is. So moving along, how thick is the largest flange? Okay, well, which one is the largest flange? Remember, the size is the diameter. The largest flange is the bottom flange. How thick is it? 0.44. So right here, this equals 0.44. All right, question 7. I didn't assign that at this point in time. We'll talk about this in class. Question 8. Again, we'll talk about that in class. And now we can calculate distances 1 through 13. And you're going to do this the same way we've done all along. You're going to use your ruler and the 2 views to calculate the various distances. So, number 1, distance number 1. If I transfer this up to the top view, number 1 coincides with a Y hole. What is the size of a Y hole? Well, according to the note, it's a diameter of 0.44. So there it is. It's 0.44 is number 1. Okay, number 2. Let's look at number 2. Number 2 is the distance from the OD of the flange to the center of the hole. The hole lies on this bolt hole circle right here. Okay, so we're gonna take the overall diameter, all right, and we're gonna subtract the diameter of the bolt hole circle. I'll just sketch this on here for us. And again, I'm using my mouse, so it's a little bit rough. And we're gonna divide it by 2. We want to know that distance. We're gonna subtract the two diameters, and divide it by 2. So we take the outer flange size, which is 3.5 right here. So 3.5 minus the bolt hole circle, which is 2.62, and then we're going to divide all of this by 2, and that's going to equal detail number 2. Okay, so 3.5 minus 2.62 equals 0.8 divided by 2 is 0.44. That is what number 2 dimension is right here. It's equal to 0.44. There it is. So moving along, we'll do number 3 together. Number 3 is the depth of the chamfered part of the hole. So we have a 45-degree angle. Okay. So this is 45. This is 45. This is 90. So it's a 45, 45, 90 triangle. We could picture this as, okay? And if we take this 1.2 and we subtract the 1 inch and divide by 2, we know what the length of this triangle is. So it's going to be 1.2 minus 1 divided by 2, so it's 0.1. Therefore, the other side of this, the depth, is 0.1. So the answer to 3 is 0.1. That's the answer to 3. So again, let me zoom this in. If I zoom this in for you, let's look at this. Let's set this up. So we're in a situation where we have a chamfer that's at 45 degrees. So this is 45, this is 45, this is 90. So to get this distance, we took the 1.2 and we subtracted the 1.0, and then we divided by 2. And we got this distance to be 0.1. If this is a 45, 45, 90 triangle, then this side is also 0.1. Therefore, dimension 3 is 0.1. Let's take a look at dimension number 4. Here it is. So dimension 4 is interesting because it's actually referring to that boss that's sticking out from the side of the main hub feature. Okay, so that's what it's looking for. If we use our ruler and we go down to this feature, the diameter is 0.74. So number 4 is 0.74. Let me show you on the inventor diagram. There it is there. This is what the boss is. When you look at this from the top view, it's going to be shown as a hidden line feature. Let me go to wireframe so you can see it. So there it is. So this is the boss right here, showing as these hidden lines. There it is. Okay. All right, moving along. We're on number 5 now. Dimension number 5. Where is that one? Right here. So this is similar to the previous one we looked at. There's number 5. We're going to take this diameter we're going to subtract this diameter and divide by 2 again. So the large flange is 4.76. Right here, the smaller flange is 3.5, and then we divide by 2. So 4.76 minus 3.50 divided by 2 equals, let me just do that for you, 4.76 minus 3.5 equals 1.26 divided by 2. So your answer should be 0.63. 0.63. And again, this is for dimension 5. So where's dimension number 6? Dimension 6 is pretty straightforward. There it is. It's just the distance between the bottom of the top flange and the top of the bottom flange. So we're going to take the overall of 2.5 and we'll subtract these two flange thicknesses. So 2.5 minus 0.3 minus 0.44. And what do you get? I get 2.5 minus 0.3 minus 0.44. I got 1.76. So dimension number 6 is equal to 1.76 inches. So moving along to number 7. Number 7's straightforward as well. We're going to take the overall height. Maybe I'll zoom this in here. So we're going to take the overall height again of 2.5. We want this number 7. So we're going to take this 2.5 and subtract this distance and this distance. So the top distance is 0.3. The lower distance is again the depth of this 1.364 diameter bore. So the depth is 0.6. This one's 0.3. So 2.5 minus 0.3 minus 0.6, essentially it's 0.9. We get that's equal to 1.4 inches. So 7 is equal to 1.4 inches. Number 8. So number 8, you can handle this one on your own. Number 8, you're just going to take the two diameters, this one and this one, and you're going to subtract them and then divide them by 2. Number 9 is the same sort of deal. You're going to take the bolt hole circle on the bottom flange and subtract it from the size of the bolt hole circle on the top flange and divide it by 2. So we can just do that one real quickly actually. So the bolt hole circle of the bottom flange is 3.86. That's specified right here, right? Equally spaced on a 3.86 diameter bolt hole circle. Then I'll subtract that by the bolt hole circle on the top flange, 2.62, and then we'll just divide that by 2, and from that we get, let me just punch those numbers in, 3.86 minus 2.62 equals 1.24 divided by 2 is 0.62. That's dimension number 9. So number 10 is actually similar to number 2 because we're going from essentially the bolt hole circle. So wherever we see a center line through a hole, we're going from the bolt hole circle to, in this case, the outer flange. And on number 2, we went from the bolt hole circle to the OD of the upper flange or the top flange. So that's number 10. Number 11 is straightforward. You're going to take the 4.76 overall. You're going to subtract 1.74, which is the diameter of the central portion of this body. So that's going to be 4.76 minus 1.74, and you're going to divide that by 2. So that would equal 4.76 minus 1.74, 3.02 divided by 2 is 1.51. So 11 equals 1.51. This is number 11. Okay? 12 is the same type of question. So, and then the last one, number 13, where is that one? 13, I will leave that to you, but the answer to 13 is, so I'll just write this down, 13 is equal to 0.182. So I hope you have some fun with this activity. This is a real good example of various circular features and how we locate and size them. So do the activity and let me know if you have any questions. I'll see you in